First one says, what is the chance of getting a 4 and then a queen? So they're talking about a sequence of outcomes here. And we're going to draw from a deck, get a card, then replace it, and then draw again. So whenever we're finding a sequence of things, the AND formula is the thing to use. So the formula says that we need to come up with two probabilities that we can multiply in a row here to get this answer. And so what we want is the probability of A times the probability of B given A. That's how you do a sequence. You find the chance of the first thing happening, and then you find the chance of the second thing happening given that the first thing happens. That's defining a sequence mathematically. So our sequence is going to be, we want any 4 first. So we need the probability of a 4. And then we need the probability of getting a queen given that a 4 was removed and replaced. And that matters, as we saw in the past. I'll do a little example on the side. Let's say I've got some marbles in a bin, like blue, green, and then red. And let's say I want the sequence blue, then red. So I'm going to pull 2 marbles out of the bin. I want to know what the probabilities are of these things happening. So I need to find the probability of blue and then multiply it by the probability of red given that blue was removed. But here's the thing. This particular question, I'm going to remove a blue, but then I'll just put it back. Okay, now we know that these events, picking a blue and then picking a red after it, would they be independent or dependent events? Independent, yeah, they are. Because you're replacing it, so the probabilities don't change. Okay, what's the chance of getting blue here? I say 2 out of 4. So I want to put that in the blank. That is the chance of just reaching in and getting any blue marble. Then you pull the marble out. So it comes out here. And now you're going to put it back. Put it back in. Now I need to know, given that blue was taken out and put back in, we know the probabilities don't change when you do that. What's the probability now of getting red, given that blue was removed and replaced? 1 out of 4, right? Yeah, so just 1 out of 4, and you just multiply them. Okay, so yeah, type it in like this. 2 times 1 over 4 is one option. Or you can do 2/4 times 1 over 4. That would work as well. Yeah, so anybody who's below gets divided. Anybody who's above gets multiplied. And we would get, it would be, 2 on top, and then 16 on bottom. So final answer, 1/8, it looks like. Alright, that's my example. So just check your calculation for this one. Alright, so you should have 1 out of 13 here, or perhaps 4 out of 52 would work, because there are 4 4s. And then what about over here? What would be the probability of getting a queen? 4 out of 52. So multiply straight across, you get 16 on top, and 52 times 52 makes 2704. That's our answer. We could change it to a decimal if we want, but it's not necessary. Approximately 0.00592. Alright, now, we want to do the same thing. This time, though, it's not going to be replaced. They want to know the chance of getting a 4 and then getting a queen. So, probability of 4 times the probability of queen, given that 4 was removed and not replaced. So what's the chance of getting a 4 on the first draw? Yeah, 1/13 or 4 out of 52, yep. What's the chance of getting a queen now that a 4 has been removed? Yeah, 4 out of 51 actually, because one of the cards is taken away now and it's not going to be put back. So you only have 51 cards left to choose from, but 4 of those still are queens because you assumed that it was a 4 that was taken out, you know. So what does that make? It makes 16 out of 2652, it looks like. And it's a slightly different probability. This chance is 0.00603. So what about B? Is it independent or dependent when you talk about getting a 4 and then getting a queen afterwards? Yeah, it's dependent because you're taking a card away, you're changing the probabilities. Yeah, okay. Alright, so C is a little bit different. It just says, what if you have probability of A being 0.24 and probability of B is 0.45? Find the chance that both A and B will occur. Alright, so there's a special case for independent events that you got to be aware of. So for independent events, the probability of B given A just is the probability of B. Because it doesn't matter whether A happens or not when it comes to B happening. And the reverse would also be true. The probability of A given B is just going to be the probability of A. So, since these events are independent, when you go to do the formula, probability of A and B, we just want to multiply the probability of A times the probability of, we would often use the form of B given A, but in this case, because they're independent, that simplifies to just probability of A times probability of B. And it doesn't matter whether A happens or not when it comes to the second probability you put in. So it's a fairly easy one. We just have to multiply their probabilities. So 0.24 times 0.45. I get 0.108. Alright. D is similar, except we have 3 outcomes to think about. So, how many blanks should we make for this problem? And before there were 2 blanks because we had 2 probabilities. Yeah, we need 3 because they're talking about choosing 3 people. It says if the probability that a person has brown eyes is 0.25, what would be the probability of getting 3 people in a row selected randomly that have brown eyes? And this is with replacement. So with replacement should make you think, what, independent or dependent? Independent. When just like the cards above, when we replace the cards, the probabilities stay the same. So the probability of B is not affected by A. But if we don't replace, then we see here that the probability of B is affected by A happening. So that is the thing. Now, these are going to be independent because of the replacement idea. So it doesn't matter who gets picked for the first, the first choice. That's not going to affect who could get picked for the next blank. So the 0.25 is not going to change with each choice. So what do we put in the blank? If you want the chance of getting one person, the first choice having brown eyes. Yeah, 0.25 for the first person. It's a 1 in 4 chance that they'll select a person with brown eyes. And now we need the probability of the second person having brown eyes. Yeah, because the chance of getting any one person with those brown eyes on any pick is going to stay the same. You could even draw a tree for it, like, because the number is easy to work with. You could have just 4 branches where one out of the 4 is brown eyes. And so, these other ones could be anything. It doesn't say what they were, but just not brown. And then if you do pick somebody with brown eyes, then you got to go on to pick that second choice. And the tree is going to stay the same because the percentages don't change. And so we just want to do 0.25 times 0.25 times 0.25. 1/4 times a fourth times a fourth, which is 1 in 64. 0.0156.